Okay, so Jan, I just want to go over the experiment that we're going to do with our period on, I guess it'll be our, what will it be? It will be our period 8 group on Monday. This is the one that Tyler, you and I had all discussed on Friday. I made up the worksheet. It's on the Google Drive. It's NL6B. The reason I called it 6B is because 6 was the Push Coast Lab, and this is the replacement for the Push Coast Lab that I wanted to do just with the period 8 group, because I think it gets the idea across simpler and better than the Push Coast Lab does. Now, if this goes great and the kids love it, I'm certainly open to the possibility of doing it with period 6 the next day. However, based on time and just wanting to get the test done before Thanksgiving, maybe we would want to just skip ahead with period 6. You might recognize one idea in this lab, which is it. I actually was thinking a little bit about the lab that you said you did at the Modeling Institute, where someone sat on a cart, a dolly, and then you had a giant spring scale and they held on to it, and you had to pull them and maintain a constant force. And you saw that you had to speed up in order to maintain the constant force. So this lab is a little bit like a miniature version of that, where each group can kind of do that on their own with one of these carts. It'd be really cool if we had a big dolly to do this on, which I might be able to get one actually for Monday, because we need one for robotics. So I could actually pick one up at Lowe's. But the other thing is that I don't know if we have a big spring scale quite like that one that you probably use with the huge dial. Chris might have one, but I'm not certain. But that would be a cool thing to do out in the hallway, which I'm sure the general kids would love. Um, but anyway, as far as this mini one goes, that I want to show you, each group is going to have one of those Pasco carts on a track, and instead of pushing it with their hand, I thought they could hook a spring scale on there, and we tell them maintain a force of 4 newtons on the cart. And in order to do that, they see that they have to constantly be speeding the cart up, just like what you guys did at the Modeling Institute. So, um, as far as the groups go for the kids, I don't know if we should just have them pick up. Maybe I'll just have them use the same groups that they've used before. The period 8 group seems to work pretty well. All right, but let me just show you. So you might not be able to read all this writing because the font's a little small, but the general idea is they've got their cart. The cart, I tell them they're going to put 2 mass bars on top of it so that it's a little bit heavier. It's 7.5 newtons being pulled down, 7.5 newtons being pulled up, and they've got to pull it with the spring scale, so that the spring scale is constantly reading 4 newtons. And what they're going to figure out as they play around with this is that they've got to speed up in order to keep the spring scale reading at 4 newtons. So I asked them to, list the objects that interact with the cart. So that's the track, the earth, and the spring scale. And then to draw a force diagram for the cart. So you've got the track pushing up, you've got the earth pulling down, and then you've got the spring scale pulling to the right. And then their motion diagram is going to be, the kind of the critical thing where they should realize that it's got to be speeding up, which is what you saw at the institute. And then they should know that the acceleration is to the right. So they see that, right, if you have a unbalanced force on it, it's going to be to the right. Now, I asked them 2 questions afterwards, or we're going to ask them 2 questions afterwards, which is basically the idea is if you have a balanced force on an object, does it create an acceleration in the same direction? And if you have an unbalanced force on an object, do you get an acceleration in the same direction? So what's the critical thing? The balanced forces giving you the acceleration, or is it that the unbalanced force gives you the acceleration? Okay? All right, so I want you to think about that question, and you can maybe try filling this in on your own. The second experiment is a really good experiment, except it's probably going to be a little tricky for the students to do it quite right at their desk. In this case, what they're doing is they're pulling on the cart still with the spring scale, but they're using it to slow the cart down. So you have to kind of imagine that they give the cart an initial push, the spring scale is already hooked onto it, and then they use the spring scale to gradually bring the cart to a stop, and they have to do it so that they maintain 4 newtons of force on the spring scale. So someone's going to kind of have to shove this. So if you see my pointer here, someone's going to have to give the cart a shove to the right so it's moving to the right. Their spring scale is going to be pulling backwards, and they have to kind of pull gently on it so that it maintains 4 newtons, and the cart is going to gradually slow down. Unfortunately, I can't try this out on my own. Maybe if this is a complete disaster, well, I think it'll be good for the kids to try, but they can always take the spring scale off and just push with their fingers to slow it down also. So again, the objects pulling on the object car are this, right? And then this is their force diagram, and their motion diagram is going to be for it slowing down, and the acceleration's in that direction. Okay? And so the idea is, again, that the unbalanced force is causing the acceleration. And all right, so an unbalanced force causes an acceleration. 2 questions. Do forces that are balanced cause acceleration? Do forces that are unbalanced cause acceleration? This is kind of based on what they've seen in the first 2 experiments. So they're kind of summarizing here. And then it asks them, what would happen if you gave the cart a push and then let go, so the cart didn't have any object pushing or pulling on it, it just had the track pushing up and the earth pulling down? What do you think is going to happen? So fill out your diagram before you do the experiment. Now it looks like I already have it filled out on the slide for you. So you've got the track and the earth, the forces are balanced, and so they should, based on what they thought before, they should know that the balanced force will cause no acceleration. So their motion diagram is just going to be for constant velocity. So anyway, that's what they do at their lab stations. And the big idea here is, in acceleration, when you have an unbalanced force on an object, you get a acceleration. When you have an unbalanced force, you don't have an acceleration. And that you don't need a force for constant motion, right? You need a force for acceleration. Now, I did put at the bottom of the sheet something that I called challenge problems, which were in that POOM material for this lesson. I didn't want to make it required, but I thought they were really good questions, and I think that some of our good students who fly through this would enjoy challenging themselves. And I hope that, maybe even if the kids ask, can we take this home and, try out the challenge problems, they might even want to, or a couple of them might want to. If we look at the first challenge problem, the idea here is that it says your friend drops a bowling ball into your hand and you kind of catch them. Now you kind of have to imagine what happens to the bowling ball as you're slowing it down with your hand. And so your motion diagram, right, is going to be, it's slowing down as you catch it. So the tricky thing here is that when you touch the bowling ball, your hands, it doesn't instantly stop. It slows down, and your hands kind of move down a little bit as you're slowing it down. It'd be really nice if I had a video to show this, because maybe it's kind of hard for the kids to realize that your hands do move down a little bit when you catch it. But the ball's slowing down, your acceleration is in the opposite direction because you're slowing down. And then if they drew a force diagram, they know that their unbalanced force has to be up because they know their acceleration is up. So they've got to exert a bigger force on the ball upwards than the earth downwards. And then the C asks, well, how could you find out if you really do have to exert a bigger force upwards on the ball than the force of the earth downwards? And the kids might say, oh, I can feel that I have to push up more than the earth's pulling down because I can feel it in my hands. There are these videos here that we could show them. So this actually is Eugenia, who I'm sure you've heard about. And here's a video of them dropping a ball on a scale. And then in the second video here, right, you notice that when the ball hits it, this is like a 20-pound bowling ball that hits it. And when the ball does hit it, let me go back. You notice that the scale has to push up with a much larger force, 60 pounds, in order to stop the ball. And so the force up has to be bigger than the force down in order to stop the ball. And so that would be kind of a cool, that's something that maybe I'll adjust the handout and put the links into this at the bottom of the sheet so that if the kids are curious and at home want to watch these videos, they can try it out. And then there's also I think there's one other challenge problem I put on the bottom about throwing a baseball up in the air that they might enjoy. But they're certainly not necessary for the kids to do in order to move on to the next lesson on Tuesday, which I know Tyler is working on writing. Okay, so that's the big idea. You're certainly welcome to call me or anything if you want to go over any part of the sheet. All right.